Hi everyone, I'm filming another video, and something you might notice is that it's silent in the background. And that's because it's finally cold enough where I can film without having the AC unit going, so that's good. So anyways, yeah, so we're going to talk about more about semi-direct products and stuff. But first, let's just note that if we have G as the semi-direct product of H and Hx equals Xh for all H and H and for all N and N, that should be X and N. Then in this case, it turns out that G is the direct product of H and N, i.e. G is a direct product and so you can either define direct products in this fashion, or you can just do the naive thing which you would learn in a first course in group theory, where you have H semi-direct product, or the direct product of H and N is just the set of all pairs H N, or Hx, where H is an H and X is X is an N. And here we have H1 X1 times H2 X2 equals just H1 H2 X1 X2. So really, for direct products, you're really just taking two groups and sticking them together. Whereas with semi-direct products, there's a much more complicated definition behind that. But as we'll see, there are some results about a semi-direct product that make it a natural thing to consider. Man, that did not erase quite as well as I was hoping. There we go. Okay, so I'm going to have another note here. Direct products look like, and you can verify this using the proposition that we did in the last video. We have 1 going to N, going to H, direct product with N, going to N, no, H, that should be H. This is phi, this is psi. And that should not be H, that should be 1. And what do we know about this? These maps are actually very nice, or very easy to write down. Phi of an element X and N is just going to go to, so the identity in H, comma X. And we have psi of Hx is just going to project the H component. And so this is just going to be H. Okay. Such a short exact sequence is trivial. And this is sort of a strange, because typically trivial, there's sort of an intuition behind that. Like if something's trivial, that means it's boring. So why is this boring? The reason that this is boring is that this short exact sequence doesn't really tell us anything about H and N. Like there's no real relation between H and N. There's nothing, they're not related in any special way. Really what you're just doing is you're taking N and you're being like, okay, so let's go from 1 to N, and then from here to here, we'll just add the identity element onto it. And so N doesn't really, Yeah, so you just have that, and then the other side you just say, oh, okay, so let's take everything, let's just project onto H and go here. And the main point is, so long as psi is, well, let's see here, phi is always going to be injective, right? Because this is just the identity map in this component, and so it's isomorphic in that component. And then similarly here, it's the identity in this component. So really the thing is, you could just take, here's the main thing, you could just take any two groups you want and just stick them together using this product here, and you get the short exact sequence. And so there's not really anything special going on here. You could do this with any two groups, N and H. Okay, so now we have a definition. So last time we talked about having sections, which is a map going this way that gives you the identity. What if we had something over here that would give you the identity? What could we do with that? Is there anything interesting about that? Is there any reason why we should study that? So here what we say is a retraction R from G to N, it's a retraction of a short exact sequence, is a HOM such that if we take, let's see here, which way I say it. If we take R and we compose it with phi, then this is the identity on N. So you start at N and you go to H, you go to G, or you go to, here, let's say this a short exact sequence, 1 to N to G to H to 1, and this is going to be phi here. And so what you do is phi takes you from N to G, but then R takes you back to N in such a way that composing the two gives you the identity isomorphism. Well, it's not an isomorphism set-wise. It's an isomorphism onto the image of an NG under phi, but that's it. So here's the proposition about retractions. The proposition. First, let's make an observation, actually. So is there any, what relationship do we have between retractions and trivial short exact sequences? What relation is there, if any? So the first thing is that trivial short exact sequences have retractions. And I say that's an observation and not a proposition because let's prove it. So we have this map phi that takes n into h cross n by phi of x equals e of h and then x. So if we want a retraction, we just take an element h comma x, and instead of we do the same thing that we did here when we projected onto h, but we just project back onto n. So we take we take r, and r evaluated at h comma x will give you x. And clearly that's a group homomorphism, and if you compose r with phi, then let's see here, if you start at x, phi is going to take you to e h comma x, and then r will take you back to x, and so it's the identity. And so therefore, there's a very natural way to get a retraction here. But turns out, we have to prove this, but it turns out the reverse is also true. So if a short exact sequence has a retraction, then it is trivial. Okay, and I think I might have enough time to prove this. Okay, so proof. So let our short exact sequence be 1 goes to n, goes by phi to g, which goes by psi to h, which goes to 1. And r, our retraction. We're going to define a new map. Define eta from G to H direct product with N by eta of G is going to be equal to psi of G, comma Rg, which makes sense because you just take this element and you just put together the two things that you'd get if you were to map into N and into H. So I claim eta is an isomorphism. And then that will basically give us the desired result, because if we have 1 goes to n, goes to g, goes to h, goes to 1, if this is a short exact sequence, let's see here, in order to have this be trivial, we want the thing in the middle to not be g, but to be h cross n. Or, yeah, h direct product with n. So what we're going to do is we're going to go from 1 to n. Instead of going from n to g, we're going to go from n to h cross n. And we're going to do that by first going through phi and then going through eta, because that will take us here. And then from h cross n, because eta is an isomorphism, we'll first go through eta inverse and then through psi, and that will take us to h, then to 1. Okay, so let's do this. Eta is a hom since psi and RR. Man, I have RR and R hour and RR in the same proof. That's kind of interesting. So anyways, this is sort of clear. You can see, like, if you were to put two things together, like eta of G1, G2, then you get psi G1, G2, R G1, G2, and then you'd break them up in here, and then you'd break that up out there. Well, right, because the that's how multiplication is defined in the h cross n, like I discussed earlier. So anyway, so that's true. For surjectivity, gonna let h comma x be in h cross n, and we need to find a g tilde such that eta sends this g tilde to xh. So first we're going to let g and g, we're going to use g to arrive at this thing that we want. So we're going to let this be such that psi of g equals h, which exists by surjectivity. Surjectivity of psi, which we know because this is a short exact sequence. Okay, so psi is surjective. So now we're going to let g tilde be g times, here, let's write it this way. So we're going to take phi and evaluate it at r of g, and we're going to take this thing inverse and multiply this by phi of x, which we see is an element of g, because how did we get this. It's just a multiplication of things that are in G. So clearly that's in G. Okay, so let's continue. What happens if we take psi of G tilde? Psi of G tilde is going to be psi of G, which is H. And why is this? This is since G tilde is in G times the image of phi, right? Because this is, G tilde is G times things which are like phi of something times phi of something. And of course this is phi of something but inverse, but of course it's a subgroup, so it's also in the image. But because this is a short exact sequence, this is G times the kernel of psi. I hope you know what I mean here by this is like this is a collection of all elements of the form G times something in image of phi, and the same thing here, but with kernel. So since G tilde is G times of something in the kernel, and since psi is a homomorphism, when you apply psi to this, the psi of G tilde is psi of G times psi of kernel of psi, right, times psi of something that's in the kernel of psi. And since that's in the kernel of psi, that's going to be 0, and so we just get psi of G. And psi of G, it was chosen to be H. Okay? So there's that. Also, what is R of G tilde? Well, let's see here. This is, we know that R of phi is the identity. And so R of phi is going to cancel here, and then we're going to be left, well, first of all, we're going to get R of G, and then here, the R and the phi on the outside are going to cancel, and then we're going to be left with the R on the inside, and bringing this inverse in there is, we're going to have RG inverse. And then we're also going to have R of phi of x. Of course, we're distributing that through because R is a homomorphism. So R of G of x, well, that's just going to be x. But we have RG times RG inverse, which is just the identity, and so this is x. So eta G tilde is, well, let's see here. It's psi of G tilde and R of G tilde, which is what? That's exactly what we want, hx. So hence, eta is surjective. Oh man, I really gotta hurry up there. Next, let G be in the kernel of eta. So eta G equals n. So the identity in H and the identity in n. So psi of G is going to equal EH, and R of G is going to equal EN. Okay, so we got that. So then G is in the kernel of psi, right? Right, because psi of G is EH, so it's in the kernel of psi, which is the image of phi. So if G is in the image of phi, then G must be phi of x for some x in n. Okay? So also we have En, which is R of G, because of this right here. So En is R of G, but G is phi of x. So this is R of phi of x, but R of phi, remember, is the identity map. So this is x. So what? So G equals phi of x, equals phi of En, because En equals x. But here, phi is a homomorphism, so this is just the identity element in G. Right? Hence, eta is an isomorphism. Therefore, 1 going to n, and we're going to go to h cross n, and this map here, this is going to be phi composed with, no, it's going to be eta composed with phi, because we go through phi first, and then through eta. And then here we have to first go backwards through, eta before going through psi. This is going to be h, this is 1, and so this is going to be exactly what we want. But we're actually not quite done, I don't think, because what we need is, we need this map. So let's see if we can fit this. What is eta of phi of an element x? So phi is going to send it to just some element in G, and then eta let's see here. Eta of phi of x, this is going to be equal to psi of phi of x, comma, r of phi of x, which is equal to the identity element x, because psi of phi, because this is a short exact sequence here, so anything that started here will die once you go through twice, and so it'll just be the identity. Then of course this is the identity map, and so this is just x. And you know, all we need, I think, is the existence of such a short exact sequence, then maybe we could just throw this out and just replace it with the natural projection. So yeah, let's do that. Let's take this and replace it with the projection pi. And obviously this is a homomorphism. Obviously this is a homomorphism that has a retraction R. The retraction R there is, let's see here, we have a retraction going from G backwards through N by R. And so what we're going to do is we're going to take our element of H. Yeah, okay, so the backwards map is just projecting the element X, because obviously if you let this backwards map, let's call it R prime, to not confuse it with this R down here. If we call this R prime, and that it just sends an element H comma X to X, then obviously that's a homomorphism, but we need to check that composing with this, that this composed with this will be the identity. But we just calculated here that eta of phi of x is e.g. x, and so if we send this through R prime, it's just going to give us x, which is what we started with. And so this R prime, this is indeed a retraction. And so all we need left is that this sequence be exact at this middle point, because we kind of messed around with this map and this map here, so we're not quite sure if this is going to work out. Oh, and obviously this composition, this is going to be an injective map. Is that what we need? Yeah, it's going to be an injective map because eta is injective because that's a short exact, no, phi is injective because that's a short exact sequence. This is injective because it's an isomorphism. And obviously we know that projections are always surjective, at least in the way that we're defining them and using them. And so, anyways, the last thing we need here is we need exactness at h cross n, and that's true because from the above we see that the image of eta of phi is, well, look, we have just things of the form e.g. comma x, where x is an n, and so that's going to be equal to n, but anything in n here is going to be projected onto the, well, actually, if we keep this like this, then this is what n looks like here, and anything in here is going to be projected onto the identity element here, because we're just going to keep that. And so this is the kernel of pi. And so therefore this is indeed a short exact sequence, and it does have a retraction there. Okay, so sorry that at the end there that I got a little confused on how to do that, but there we go. That will complete our proof.